Hey everybody, welcome back to HPC Tech Shorts, where every week we take you to the HPC engineering water cooler here in AWS so we can talk to the nerds and the other technologists who are making AWS the best place to do your HPC in the cloud. I'm very excited this week to be joined by Sean Smith in Seattle and Evan Bollig in Minneapolis. Hey guys.
Hey Boof, thanks for having us.
Hey Boof.
So both of you now, Evan and Sean are both HPC specialist architects in our organization, and they work with loads and loads of customers every day who are trying to solve some pretty complex problems. So now lockdown, of course, lockdown is, we're all experiencing this globally. Lockdown is because of COVID, and lots and lots of things that we've been doing in the last 12 months have been driven by COVID. Response to COVID, not just working at home and doing lots of virtual things, but lots of workloads we've been running for customers who needed to drop everything and solve some really gnarly problems very quickly. Now, as far as I can tell, Sean, that's one of the things that really drove the NoTears cluster project into existence. So do you want to maybe give us some background on how that happened, but also tell us about NoTears?
Sure. So early last year, in early 2020, we were faced with the COVID-19 virus taking over the world. And we started thinking about what we could do about that. So one of the early things that we did is AWS joined the COVID-19 HPC Consortium. So that was a group of the leading academic and industry HPC centers with the goal of giving access to researchers to the best computing power and the best resources so that we could really accelerate that research into COVID-19 and I think some of the rapid rollout of the vaccines has been proof of that working.
Yeah. So I know that the Moderna have spoken quite favorably about their use of the cloud in their research, because they set up an entire simulated chemistry lab for all of their researchers to use, so they could actually design molecules inside the cloud and do it very quickly. That makes a big difference to that time to science. This is when time to science really made a big difference for us all.
Alrighty, so like I mentioned, with the COVID-19 initiative, we had a challenge. We had to onboard a lot of researchers, some of whom had no experience with running HPC workloads in the cloud, onto AWS quickly, and make it easy for them to get started without having to know the nuts and bolts of how everything worked. So what we built was a solution called NoTears cluster. Here's what the architecture looks like, and this looks complicated, but we'll go through it, and it's actually quite simple to set up, as Evan will show us later. So what NoTears creates for you is it creates a traditional cluster where you've got a head node running Slurm as a scheduler. It has SPAC as a package manager, which pulls from a binary cache, and then it's got a couple different queues. So it's got an EFA queue. That's for tightly coupled MPI type jobs. It's got a GPU accelerated queue, and then it's got a spot queue to take advantage of the secondary spot market. All of this is orchestrated with a managed Lustre file system from FSx Lustre, and this allows you to import and export your research data into S3 and back that up between runs. So Evan, if you want to,
this is a supercomputer in a box, right?
Yeah.
The kind of facility that most researchers would be applying for merit allocation time on at a national facility, but they're getting their own personal one by clicking on a button. I mean, is it that simple?
It really is. Right. Yeah. So sorry to interrupt you, Sean. It really is, Boof. When you can just click to launch this solution, and you get all of your compute figured out, the networking figured out, and all the storage. Even remote desktop here is a solved problem for the end users.
Right. You don't get remote desktops on national HPC clusters, by the way.
Right.
That's kind of not the done thing. No one's going to give you the root password to go and install VNC on the supercomputer head node. So that's there's a lot of stuff going on here that people just can't do elsewhere. So Sean, EFA versus non-EFA, just very quickly, split the difference for us.
Yeah, so EFA is for tightly coupled applications, like think computational fluid dynamics, where each of the processes on the instance need to talk to each other with low latency and high bandwidth. And then a non-EFA queue would be for something like a genomics workload, where you can break up your parts into what we like to call embarrassingly parallel components, and each of those can be split out onto a different machine that can do the computation in parallel. So parallel cluster provides a lot of the components, like the operating system. You can choose between your favorite OS, such as CentOS or Amazon Linux, and the scheduler, as well as the file system components. But the way this is presented to you, it can be quite overwhelming and hard to set up for an individual researcher. So we set out to create the easy button to make it launch in our own opinionated way. We realized that researchers are not research IT, and researchers really care about their research and not the underlying infrastructure. They want to get it set up, and they want it to be optimally set up, but not have a lot of headache or heartache in doing that.
Most researchers don't particularly care whether they're using Slurm or SGE, as long as it works, right?
Well, that's just
and
it. Right?
They don't even want to know what FSX or EFS or S3 is, right? They just want that out of the way.
They just need some place to do their compute, and oftentimes they are even accustomed to working in data center or working on systems at institutions where research IT has already provided the applications themselves. So all they do is sign into the computer and start the job. They don't even need to worry about installation.
So this gets them to their molecular dynamics workload really quickly. Yeah.
So the NoTears solution is on GitHub, and basically what any user would need to do is just go to the GitHub URL, which we'll post in the notes for today.
Put in the show notes. Yeah.
When you go to that URL, you're presented with a lot of code and some crazy commit messages. I'm sorry about that. But down here toward the bottom, you see the README, and we've got a number of buttons that you can click to do the quick launch. So you basically choose your desired region, and you can just click to launch. This takes you into our CloudFormation service. If you're not logged into your AWS account yet, it'll prompt you to authenticate. You sign in, and then here you can create a cluster by choosing a number of configuration options. Everything is pre-populated. You can just scroll to the bottom and go if you'd like, or you can make some choices like choosing your operating system if you wanted to go between Amazon Linux 2 or Ubuntu 18.04, for example. You can configure your FSX cluster file system. Say you want to change your performance from 100 megabytes per second per terabyte to 200 megabytes per second per terabyte. And then, it's as simple as acknowledging that you'll create resources and, sorry, I got my screen in the way here, create stack.
And we've lost your face.
Oh, sorry.
Oh, there we are. Cool. Excellent. So there's a bunch of there's a whole ton of magic that just went past there. Like one of the things that you showed was, I'm going to decide how much performance I want out of my FSX Lustre file system. I want 200. Right?
Yeah. So let's go back in there again, and we can take a deeper dive.
That's really cool.
Yep. So we provide knobs to turn. You don't have to turn them, but it does give you a lot of control over what happens. And if you recall that architectural diagram, the FSX Lustre is it's actually created outside of parallel cluster. So when we get into our stack, what we're going to see is that we can create multiple clusters with the same file system and share data across them. So it really, it's important that when you create your first cluster, you take the time to think about what the performance profile will be that you'll want. And if you need to change anything, you can always go back and apply that as a change set on the CloudFormation template.
That's really cool. That is really cool. And the other one that I thought was interesting there is the choice of Linux. I mean, what's key there is if somebody's doing a lot of machine learning development, like they're developing models and they really need Ubuntu because, that's the environment they're used to working in, they can just have it, right?
That's right. So we leverage the power of parallel clusters post-install scripts to provision these stacks after they've booted, and our post-install script is actually it supports Amazon Linux, CentOS, Ubuntu. We try to keep that paired with whatever the support is for parallel cluster. So here I've loaded up a running Cloud9 instance for the NoTears cluster. This is the same link that you would follow from your CloudFormation stack when it completes. And a few things that we're looking at here. First, we've got a config file that's provided, which gives you sort of a reference on how to configure parallel cluster with all the details for the queue settings, DCV settings, post-install, all of that stuff figured out so that you can modify this file and update your cluster, or you can go ahead and create new clusters from it and tweak it to whatever you need in terms of size for the queues. Here we've got a queue size of 16 nodes, a minimum count of 0, which means that whenever possible, parallel cluster is going to spin down your compute pool if there are no jobs in the queue and try and conserve your compute resources, conserve your spend, and then spin up to 16 nodes for whatever capacity you have or whatever demands you have in your jobs.
That's cool.
Yep.
So sorry, Evan, I just wanted to point out, so this is running in your browser, correct? So you could do this from any sort of machine like an iPad or a really thin notebook, and have access to that same computational power.
Yeah, that's indeed. And what we're going to see, even with the remote desktop, that's an option as well.
You could have a Jupyter notebook running in one tab and an HPC cluster running in another. That's really neat.
That's right. That's right. So here in the bottom right, we've got a full terminal. This is a full Linux terminal, and we've actually got the parallel cluster software pre-installed. So you can do something like pcluster list, and you can see that we've got an existing HPC cluster. Now, I'll just use pcluster SSH to access that cluster right away. If anyone has played with parallel cluster in the past, they may have run into an issue where they have to create SSH keys. We've taken care of that already. So it's more or less passed through into your cluster. You get straight in, and you can do things like SQ to see that, well, I have no jobs running yet, but we'll get there. And let's say I do an srun minus N2 on host name, right? Something super simple. I've got, with my cluster, I've got a couple of nodes that can actually execute, and they're currently, because the job is finished, they're in an idle state. And you'll notice the difference here, the idle with a tilde, that actually indicates that these nodes are ephemeral. So we have 4 different partitions with up to 16 nodes of compute capacity, but in this case, only 2 of them are actually running, and they will spin down after a timeout when my jobs have completed and 10 or 15 minutes have passed.
That by the way, that's going to be something quite non-intuitive to anybody who's never used the cloud before, but that's how we roll. We expand and shrink the infrastructure as needed when it's needed, and when it isn't needed, it just doesn't have to be there.
That's right.
And this is doing all of that magic in the back so that you don't have to do it yourself or think about or calculate anything yourself.
That's right. Cool. So that's parallel cluster provided functionality with Slurm. Some other parallel cluster provided functionality here. If you follow our tutorials, you may see that you have to run module avail, right? you'll see that with Parallel Cluster, there are a number of packages that are provided: libfabric, OpenMPI, Intel MPI.
Mm-hmm.
And in this demo, I've got a load of packages up here that might seem confusing. They won't be available out of the box with NoTears, but for the sake of time, I pre-baked things like Emerald. I wanted to make sure that we had something somewhere to start. And the way that I got those is NoTears actually comes with the SPAC package manager pre-installed.
SPAC is, by the way, one of the best things to ever happen in HPC. Let me just
it really is. SPAC has over 5,000 HPC packages available to build and install on your clusters. You can say SPAC list, and you can see all of those different packages. You can choose one and say SPAC install let's say Reliant, right? And
this is a cryo-EM package, right?
This is a cryo-EM package. This actually came up in one of our HPC tech shorts the other day. Yep. And what you can see is that I've got a number of packages that are pre-installed. So SPAC skips over those and goes straight to installing a missing dependency, and it'll configure all those details and install that for me. Now, let's say I want to install a package that's heavily used or frequently used. The NoTears solution actually comes with something called the SPAC binary cache enabled, and this is an S3 bucket that AWS and the SPAC team are jointly curating, where we pre-build a number of packages and different versions so that users can actually just go straight to installing from pre-built binaries as opposed to compiling from source every time.
Yep. And by the way, thanks to Intel, most of these binaries in here are getting compiled with the Intel compiler and Intel MPI. So they're really performant binaries. They're really fast.
Yeah, right. And so the package itself plus all the dependencies come in, right? So if you go to install OpenFOAM, for example, we can cut the time down from a full day worth of compile to minutes worth of install time.
That is crazy good, and it's difficult to get across to folks just how important that is, because we say it in like 30 seconds that you can just go to SPAC and just install this thing in a few minutes. It kind of sounds like a consumer desktop, and yet it's an HPC cluster with really, really complicated software on it with enormous complicated dependencies. Like I say, SPAC is just one of the best things ever.
Yeah, let me give you an idea of how complicated some of these dependencies can be. With the spec command, I can say IL and then OpenFOAM, and
you have to
this
spell
should
OA. Yeah.
Foam.
Spell it the British way. Yeah.
Yep.
So there you go.
And here with OpenFOAM, it takes a minute to compute the entire graph of dependencies, and then each line that we're going to scroll through is a package that would have to be installed.
Holy moly!
Right. I'm going to move my finger down the trackpad.
This is why researchers are scared of playing around with HPC clusters, and for good reason. This is really complicated stuff.
That's right.
Anyway, SPAC rocks.
That's right. So that's available, and that helps our end users get their applications installed much faster with all of the dependencies they need. And then once you have a package installed, the SPAC configuration puts it in the module path, so you can see here all the different packages and versions, and you choose what you want, and you can just do a module load. So let's say I wanted to module load Python, and you see it pulls in the dependency tree that way as well.
And that's pretty critical, because researchers need to be able to track the provenance of their, for how their data gets treated and how the results get generated. Versions of libraries and versions of dependencies and versions of applications really matter a lot. But sometimes you want to have 2 or 3 different versions of these things living simultaneously on a cluster together, and you want to be able to switch backwards and forwards. So,
so that's a great point, Boof, and I want to expand on that a little bit, because you may think that SPAC is similar to your traditional like Yum or apt-get package manager, but it really isn't. Like, you can choose the underlying packages and versions and how you want to set up these applications, and that for a lot of people is really important. And what we've done with this collaboration with the SPAC team in building the binary cache is we've taken versions that are optimized for the AWS resources, for example, the networking that we talked about earlier, the EFA networking, and we've compiled it such that it supports those. So you're getting out of the box really good performance. And you can go in and tweak it if that's important to you.
Yeah, that's true. But you're right. It would take somebody an awful long time to get a cluster built ready to this point, and then get their applications compiled on it and get the applications compiled and built really well. Anyway, this is, I guess, at risk of this becoming the SPAC fan club, which I think we already are. We're look, this is really good. So so zooming out a bit for a minute, where do we go with this? What are the next big things that people could do with NoTears? Because you've made it one click easy. We've bottled up a lot of complexity and configuration files and all that other stuff to hide all of the junk so that somebody can get something done. What's the next big thing they can do with that?
One of the cool features that we have with the NoTears solution is that you can actually import this into a CloudFormation stack, and you can limit the number of options that you provide end users. So you could say, all right, I want all of my organization to use Amazon Linux 2, and I want everyone to use SPAC version 0.15. You can force that with CloudFormation templates this way, or you could bring your own configuration file for the post install.
Wow. You could just have a whole bunch of these prefab clusters, ready to go. One for the chemistry department, one for the physics department, or one for the bioinformatics school. Just all the number of different options you could have here is quite astounding, right?
Yeah, really, and we continue to add options here. There's a bit of a throwback here when you look at the history of parallel cluster. Version 1, it was named CFN cluster, and Sean, you could probably speak more to this, but CFN cluster was sort of the same premise, that you would have a CloudFormation template and you could customize the options and serve it out to users that way.
Yeah, and I think what's really cool about this is not only can you customize the options of the cluster, you can build other resources around it. So you can think of this NoTears cluster as a building block. It's your HPC building block. And then you can also add on, let's say you want to use API gateway so that users can submit jobs via an API call. You can add that component with the NoTears component backing it. And so you can set up an end-to-end research workflow using this.
I love it. All right. Well, I think that's probably all we've got time for this week, so that we can hit to our time contract. But thank you for coming along and showing us this. This is really cool stuff. Thank you. And actually, more to the point, thanks for building it, because I think there's going to be a whole lot of researchers around the world, particularly in the COVID space, who are going to be appreciating it. And if you think about who that matters to, there's about 7.5 billion people on the earth that it matters to, because this is one of the few things that I've seen happening in my lifetime where science has been absolutely critical to saving all of us from a big global problem. So anyway, well done. Nice work. If you, for the folks at home, if you like what you see, please click like. If you really like it, please click subscribe and share it with your friends and your colleagues.